Hello everyone and welcome to today's webinar. Before we begin, we want to cover a few housekeeping items. For any common technical issues, please refer to the Help widget located at the bottom of your screen. This webinar was pre-recorded and is being presented with a live Q&A. If you're tuning in for the initial webcast, you can submit questions via the Q&A widget on the left side of your screen. The researchers will be answering them via the widget in real time. Also, stick around after the webinar for the live Q&A, when the researchers will dive deeper on popular questions asked. Additional resources and links provided from today's presentation can be found in the resource list on the right side of your screen. An on-demand version of the webinar will be available approximately 1 day after the initial webcast and can be accessed using the same audience link that was sent to you earlier. On-demand viewers will get to hear the recorded version of the live Q&A. Enjoy the webinar.
Hi, I'm Ben Zorn, and I'm going to be talking about the next generation of developer tools for data programming. My background is that I'm a researcher in the Research and Software Engineering group inside Microsoft Research, the Redmond Lab, and my history focuses on looking at problems related to programming languages, in particular issues related to reliability, performance, and security. Today, I'm going to be focusing on a different category of user. In this case, when I say developer, I'm not talking about traditional professional developers. I'm talking about developers who use computers to solve problems. And I'll go into more detail with that. And when I talk about data programming, I'm not talking about writing code the way we traditionally think about writing code. I'm going to be focusing on the next generation of tools that allow people to use data and convert it into useful information and ideas. So before I go into that, let me give you an outline of the talk. I'm going to start by outlining briefly my notion of the history, both of the computers that we use and the tools we use to program them. The second part of the talk, I'm going to focus specifically on issues related to people using spreadsheets. And why I talk about spreadsheets is because fundamentally, I see spreadsheets as the prototype for the kind of very powerful tool that enables people that aren't necessarily professional developers to have very valuable insights and work with computers to solve their problems. And finally, I'm going to open up the discussion and look more broadly at a whole class of problems now that we're seeing where people are using computers and data together to build new kinds of experiences, new programs. And that notion of using machine learning, using AI is fundamental to the next generation of applications. But let me start by doing a little bit of history. I got my PhD thesis in 1989, and it was focused on the performance of garbage collection, which is a technique in programming languages. And as much as it was about software and software tools and algorithms, in fact, a lot of my thesis actually involved data. So I was measuring the performance of this particular approach to garbage collection. And I was looking at the trends. I was looking for patterns that I saw in the data to understand what insights I could get. And this is back in 1989, and the tools I had were quite primitive. But you can see right at the beginning of my career, I really was focused on extracting information from data. Now, 10 years later, I was at Microsoft Research. This is Building 9 on the Microsoft Research campus. It was a great building, recently torn down. But what else was true in 1999? Well, first of all, you can look at the computers that we were using. And, there's a desktop, obviously laptop. The big computers, the big iron, were things like these supercomputers, the ASCII Blue Mountain supercomputer. And in 1998, it has 6,000 processors, and it was approximately estimated to have about 3 teraflops of performance, which at the time was amazing. What kind of tools did people use to program these computers? Well, of course, as it's familiar, we knew even back then we had Visual Studio, and it was a very powerful tool, and it allowed you to actually build components using Visual Basic, et cetera. That's one of the great advantages that the PC market created, was its opportunity for many people to participate, to generate applications, et cetera. We had new languages, languages like Java, languages like JavaScript, which are just starting to show up in the market. You can see the history here. The ECMAScript, the standard around JavaScript, was created in 1998. Now let's look a little bit at data science tools. These are tools that people working with extracting insights from data were using at that time. And of course, one of the really powerful tools at the time was Excel. And this is an example of Excel 95. There were other tools on the horizon. They weren't really widely used, but they were available. One of them was a language called S, which was developed at Bell Labs. And at the time, it was really the first effort to try to focus on helping people have very specific problems around reasoning about data, doing statistical analysis of data. And it was, at the time, you probably never heard of it, but in fact, it was the genesis that actually led to the R language, the successor. Likewise, Python was in early development. One of the major releases of Python occurred in about 2000, and it really was just starting to be used more broadly than by a narrow group of people. Okay, so let's fast forward 20 years. This is now last year. Microsoft Research has moved. Now we're in Building 99, a beautiful facility. One of the things that we see now in the current generation of computers is just an enormous variety in the kinds of computers that we have. Okay, so it used to be desktops, laptops. Now we have our doorbell as a computer. Almost everything we touch these days has a computer embedded in it, and that really totally changes the kinds of things we do with computers. One of the things to look at with this slide is the amount of compute power that we have at our hands now. Things like your Apple iPhone, the next generation, estimated at 0.7 teraflops. So that's a quarter of that ASCII supercomputer we talked about in 1999. The Xbox One, 6 teraflops. That's 2 times. So every one of your Xbox One X has twice as much compute power as that giant computer that we had back in 1999. And amazingly, even your car, the estimate for the NVIDIA processor in the current generation of cars is 30 teraflops, 10 times the performance of what you had in the ASCII supercomputer. But this focus on the devices we have right now totally misses an entire generation of change that we've seen, and that's the advent of cloud computing. So as much as those are amazing devices, if you look at this is a picture of the Microsoft Quincy Data Center taken from a talk by Mark Russinovich. And it shows the scale of the compute power now that we have at our disposal for things like natural language understanding, for things like search, et cetera. And the advent of the cloud brings an enormous amount of resources, both compute, storage, and networking, into the hands of almost anyone that wants to use it. And so this is a total revolution in the capabilities of the computers we have and the kinds of problems we try to solve with them. Likewise, the tools that developers use to leverage, to harness this power have also evolved. And some of these things are still quite familiar. So, for example, we have Visual Studio, we have Visual Studio Code, both very valuable, both widely used, familiar. But we also have a whole new generation of tools that really has changed the game with respect to software developers. In particular, we have GitHub. GitHub is a great way to bring together many, many different developers to share, to exchange, to provide insights back and forth. It's a revolution in the way people share their experience around developing code. Likewise, we have now tools, because we have all the clouds and cloud computing, we have all the tools around harnessing the cloud. And so if you go to the Azure website and you start looking at all the things that you can just easily drag and drop and create new cloud instances, it's a very powerful tool set. It allows people to build systems, to test them, to deploy them, et cetera, with just a touch of a button. And finally, on top of that cloud computing infrastructure, now we have this notion of containers and the ability to package our software instances, our software systems, into larger software systems and deploy them just with a touch of a button. And so we have tools like Kubernetes around that. So the major takeaway here is that cloud computing really has changed the game, both in terms of what computers are available and how people use them. Now let's revisit. As I mentioned, we're talking about data programming, data programmers. Let's look at what data scientists have for tools. So one of the great things that programmers have today for data is Excel. In fact, if you look carefully, the interface for Excel looks very similar to what we had 20 years ago. And one of the takeaways here is that that's a positive thing in the sense that it's a stable, well-understood framing of what you need to understand data. But on the negative, as I've shown, many of these things in the world of computing have evolved dramatically. And the question becomes, how have the tools that we use to understand data evolved in the same way? So, for example, we have RStudio. S evolved into the language R, which is an open source implementation of S. And RStudio is a developer experience that allows you to write code in R and understand it. Similarly, around Python, we have a notion of notebooks, which is really an evolution of the concept of literate programming, where we have a sequence of steps that involve actually getting information, processing it, et cetera, coming to a conclusion. And these notebooks capture those steps in a way that they can be shared, which is also very valuable. But one of the things we hear when we talk to data scientists is that all the stuff that regular developers take for granted, you don't have when you move into a notebook environment. You don't have the same kinds of high-powered capabilities, say Kubernetes or GitHub, et cetera, when you're trying to do data science. And I'll drill down on that point a little more in just a minute. But let me recap. The key insight here is that in 20 years, we've seen enormous changes in the way that computers exist, how the computers work, how much power they have, and how people programming them. And yet, even though almost all the future of computing depends on understanding, capturing, understanding, and taking value out of data, the tools that we have to understand that data, to work with that data, have not evolved at the same rate. So we have all this computation, we have all this ability to think about how we might solve really hard problems using AI, ML, et cetera. But the tools that we have to do that task are still not up to the task. And so really my talk is a call to action. It's a call to action to the community, the developer community, the professional developer community, to the software engineering community, to think about a broader view of who is a developer. So traditionally we think about pro devs, professional developers, people who write C code or C++ code or Java for a living. But I want to think about growth developers. These are developers who are not the traditional C++, et cetera. They're people whose job it is to take data and get insights. We often call them data scientists. I like to think of them as a different class of developer. There's people who want to get a job done. They use a computer to solve that problem. They have to answer questions. When can I retire? How effective is this drug? What's the best crop to plant in the soil? These are all fundamental questions, and I don't want to have to be able to be a C++ programmer to answer them. And this is why I'm calling on the software engineering community to take those individuals who are trying to answer those questions as a priority, to not focus solely on the professional developers, but to expand the view of who a developer is and take into account those people. And you can ask, well, why should we do that? Well, here's the big answer. Because there are 750 million Excel users. Okay, so instead of the 50 or 10 million professional developers, we're talking about orders of magnitude more people with a much broader view of what their problems they're trying to solve. And I'll talk to that at the end of the talk. But fundamentally, the ambition for what we can do with computers has gone up enormously. And what we need to do is empower the people who can achieve those goals, reach that ambition with the right tools. Okay, so that's mostly my sort of aside about history. Let me just say one other thing about history. So fundamentally, when we think about software engineering, we think about the process of helping developers. We really focus on the code. So historically, what that means is that we write code. We say, hey, is this code right? Is that wrong? And we can see that in some of the early works. Like, for example, Niklas Wirth, a very famous programming language designer and a spokesperson about software, had a book called Algorithms Plus Data Structures Equals Programs. And let me just challenge that for directly. I personally feel like he's missing an enormous part of what programming and what building applications is, and that's the data. We can't have useful things without the data. And I think what we've seen in the history, the 30 or 40 years since this book was written, is the data makes an enormous amount of difference in terms of the ambition that we have and the kinds of ways that we think about building software. So let me step back and now focus a little bit more directly on spreadsheets. I sort of made a joke about how spreadsheets, in 1999 and spreadsheets today are kind of the same, and that's true on the surface, but of course it's not true when you dig down. For example, spreadsheets now multi-platform. You can go to any, in particular Excel, you can go to any platform and get a spreadsheet, and it works just the way you expect. There's things like collaboration, very powerful capability, multiple people working together in the same document. Here inside Microsoft Research, we've done some innovative things to empower people using spreadsheets. And this is focused particularly, again, on people who are not developers, who don't know how to write the code, but who need the power of the computer to help them. So, for example, there's a capability in Excel 2013 and later called flash fill that allows you to do programming by example, where I can do a string edit. I can extract from a string like the Jim.Smith just the company or the last name, show an example of that, and then the computer inside Excel will actually automatically determine a program that will help me complete that task for all the other strings in the email column. So that ability to program by example is very powerful because, again, it enables many more people who couldn't write the code to do that transformation to get the value of it just by showing examples. More recently, one of the things that's been added to Excel is rich data types. So instead of just numbers and strings, we actually have records, in this case, financial records, et cetera. So these tools have evolved. But what I'm going to point out in the next section is that there's still a tremendous amount of opportunity here. We're not done with the evolution of tools to help people with data. So let me focus specifically on spreadsheets because they're so widely used on the one hand, and they're also used for very important decisions. Okay, and I'll highlight this. So this news article from was it 2013 talks about a problem. It's called the London Whale, who was a trader for Morgan Stanley. And he basically made a bad trade based on a single cell in a spreadsheet having the wrong formula. And that trade, in particular, led to about a $9 billion loss. So one spreadsheet cell with one error, $9 billion. Now, if that isn't a reason to try to find bugs in spreadsheets, I can't think of another one. But that's not the only example of this situation. There are a number, you can look on the web, there are a number of cases where errors in spreadsheets resulted in bad decisions, in money lost. In particular, here's one that hits home. It was discovered a couple years ago that, in fact, biologists have been using spreadsheets, Excel spreadsheets, to store information about gene sequences. And it's a very common practice to have the spreadsheet accompany the paper. And some biologists started looking at these spreadsheets and realized that there had been an automatic conversion from the gene names, like one sept, it turns out is the name of a gene, into a calendar, into a date. And this had not been discovered, so about 20% of all the data in some of these files was actually incorrect and had been incorrectly transformed. So there's many cases where people use spreadsheets, they get a result that they didn't expect, and we'd like to help them with that. So how is it? So first of all, we know that you can build tools to help software developers. So certainly we should be able to help build tools to help spreadsheets users as well. But what are the challenges? Why is it so much harder to help people who work with spreadsheets than it is to help people who write code? And let me try to illustrate that with an example of a file. So one of the things that's very different about spreadsheets is that it combines many aspects that usually are separate. As I mentioned with code, often developers think about the code separate from the data. The data somewhere over here, they work on the code. In the case of spreadsheets, what you have is you've got a mix. You've got formulas, so often values in spreadsheets are computed, and I'll show you in just a minute how you can actually see which things are computed and which aren't, and other things which are just data that comes in. So it's a combination of code and data. But what's really unique about spreadsheets, it's totally different than normal software, normal code, is that there's also a layer of presentation. So the person who created the spreadsheet not only thought about the code and the data, they also were trying to communicate something to somebody else who was going to look at this sheet. So they add extra lines, or they underline, or they make a row bold, or they add natural language to help you understand it. And these are aspects of understanding software that traditional software analysis does not focus on at all. Okay, so this is a new challenge. So let me just highlight the differences between trying to find bugs in software and in code, and trying to find bugs in spreadsheets. So often, I mean, never with spreadsheets do you have a specification. You don't have somebody saying, this value should always be greater than 0. You don't have tests. There's no notion of a unit test for a spreadsheet. You have a very limited type system relative to a program. So a program, you can create your own types. You can do type checking, et cetera. In spreadsheets, often the values are just values. It's like there's a number. Is it euros? Is it dollars? Well, there might be formatting, but there's no underlying system that tells you, oh, you're about to add a dollar to a euro, which would be an incorrect thing to do. One of the things about spreadsheets is the degree to which spatial relations matter. And so people looking at them understand that. They understand how something at the bottom of a column probably relates to the things above it. Of course, you don't have that same notion in software. And again, as we focused, from the beginning of the talk, really we're talking about individuals who don't have the traditional software development background. They don't have the same experience writing code, debugging, testing, et cetera. And just to sort of highlight, one of the challenges is like even knowing what data goes with what is a challenge. In spreadsheets, you have a free-form approach, and so as a result, even knowing what the boundaries of, say, a table are, or whether these two things are related to each other because they're in the same table or they're separate, is not a solved problem. It's not explicit in the document. So I'm going to talk about two methods that I personally have worked on to think about how we can help developers with spreadsheets. And they involve two projects, independent approaches to solving this problem. The first approach uses statistics, and it's a tool called ExceLint. And we call it ExceLint because lint is a traditional tool that was used to find software bugs, and so ExceLint is a way to find bugs in spreadsheets. And the method for ExceLint that distinguishes it is the notion that it doesn't use a complex machine learning model. It just uses the notion of regularity and statistics to try to understand anomalies in spreadsheets. So instead of talking about it in the abstract, let's go to an example. Okay. So this is a spreadsheet from a corpus, a public domain corpus. It's basically not a real spreadsheet in the sense that it looks like some employee payroll, and it was on the web somewhere. Somebody got it, and you can immediately see in it, there's information that a human can glean. So these are probably people, the names of people. There's some calculation about, say, their taxes or how much they get, how much they take home. There's information about how many hours they worked, etc. One thing is, it's not obvious in this view, which is called the value view of the spreadsheet, which values are computed and which ones are just raw data. So the number of hours worked is probably raw data, but the total hours, that doesn't seem like that's a data. That should be computed from these other values. And so how do we know that? Well, you can go to individual cells and see if it's being computed with a formula, but one of the tricks is that there's a method. There's a view inside Excel called the formula view that actually opens up every cell and shows you the formula. Instead of the value being computed, it shows the formula used to compute it. And this view gives you more insight into the structure because now you see, okay, all these values are being computed. These are inputs. They're just the hourly rate. And then some cases you start asking, well, this is this cell times 0.15, but hey, why is this one different? There's something going on here. And what we've done with ExceLint, so let me change that view back. So again, you wouldn't notice that if you didn't have that other view, right? But what we did with ExceLint, we said there are patterns, and we're going to look for those patterns statistically. So if we type reveal structure on this sheet, all of a sudden we see some colors, and this is going to tell us something about the sheet, and it immediately makes certain relations more obvious. And so in particular, let me just walk through what some of these colors mean. There's two distinguished colors on this sheet, gray and yellow. Gray is a data value, so there's no formula being used to compute these values. And the thing with gray is it means that this is data that is somehow being used by some other formula in the sheet. So it's kind of being used. It's consumed. The thing about the yellow values is that those are values that are just there. There's nothing else that uses them. And you might ask, well, why are these even here? Well, they must be there to help somebody who's looking at the sheet because it's not not feeding into any formulas. And so that's one aspect, and that helps you understand a little bit more about how the values flow. The other thing to talk about is the colors. And what happens with the colors is ExceLint uses a different color to highlight different formula patterns. And so the formulas here are different than the formulas here are different than the formulas here. It doesn't say exactly how they're different. It just says that they're different. Now, so immediately there's some things that sort of pop out. Like this cell here is gray, which means it's a data value. All the cells below it are actually red. So this cell is probably incorrect. And in fact, what we find, it's not even computing the correct value. So in this case, we've got a cell that should be computed and is not. One of the things that ExceLint points out is, if I go here, is it will show us a case where, again, this whole column is being computed by one formula, but this one cell is being computed by a different formula. So again, there's a mismatch here, and what we're doing with this suspicious, essentially what we call suspicious ranges, is highlighting where on the sheet there are inconsistencies that a human should probably pay attention to. So that's the approach of ExceLint to finding bugs in spreadsheets. It's both using the visual system of human to find patterns that seem irregular and to understand the overall organization of the sheet, and to take advantage of certain statistical analyses to highlight anomalies that we think are particularly important. Okay, so that's ExceLint. As I mentioned, basically the focus here is going to be on two different techniques to think about finding bugs, and I've already mentioned ExceLint. Let me talk about the second technique, which is a more more complex and at this point, a little bit less mature approach to finding the same kinds of problems. And this approach is to use neural networks. Is to reason about the contents of the spreadsheet by training a neural network to recognize patterns and to identify cases where the patterns, where the sheet breaks the pattern. And just as inspiration, can think about all the work on understanding images and saying, look, we know where the faces are in an image. We have techniques, algorithmic techniques based on convolutional neural networks that will tell you what where the people are, where the faces are. And so our question was, can you apply a similar kind of approach to recognizing aspects of spreadsheets that you want to highlight? And the first work we did in this space is a project called Melford, and the idea here was to find cells in sheets, individual cells, for which the pattern is broken, and we think that it should be this cell, for example, shouldn't be a value, which it is. Like it's not. This is a formula. This should also be a formula because the column header says total. And so you would imagine this value here is the sum of these. So instead of being just a number, it should actually be a formula like sum right here. And so our question was, can we train a neural network to recognize irregularities like this and highlight them for the user? Now, I'm not going to talk about the Melford project. I'm going to talk about another project we've done, which is, has some elements of this. And I'm going to use this project, which we call Jura, to think about how we build the software that actually allows us to find these, to do this kind of analysis. And this is going to flow into the final part of my talk, where I'm going to focus on what the challenges are of building any software that incorporates AI neural network techniques. So let's talk about a separate problem, which is more of a core problem instead of an end application. It's more of a understanding structure. And the problem I'm going to talk about is, how do you find tables on a given sheet? Now, you might think, well, every sheet is a table. It's just one table. But in fact, if you look at the way that sheets are organized, in fact, often you see multiple tables on a sheet. So in this case, you can see here's a header, a bunch of column headers, and here's some values. And here's a separate header and different values. And these are independent things. And however, for whatever reason, the person who created the sheet intended for them to be separate and to be looked at differently. So for example, if you're going to generate a chart from this data, you probably don't want to combine these two. You probably want to pick one of these and then create a chart. And that's why finding the tables, finding where the tables are, is quite important. Now you might think, okay, well, couldn't you just write an algorithm that tries to find the table, some kind of heuristics, looks for, I don't know, cells that have value, like numbers in them. But you can see this example really breaks a lot of rules. Like there's empty columns, right? And you could ask, well, is this part of the table below it or not? So heuristics in general are not a good strategy. We in fact built some heuristics and found that they weren't very good at finding the actual tables. Now, so this opens the question: well, how do we solve this problem with machine learning? And one of the traditional aspects of machine learning is you have to train. So the notion is you build a model which tries to predict things, and you have to train that model with data. So you have to have actual labeled data to train the model. And a challenge that we find in this particular space is often when you think about, say, natural language understanding or image processing, the training involves hundreds of thousands of labeled samples that are used to train the network. And in our case, we didn't have 100,000 samples of sheets where the tables were labeled. And so we had to find a different way to solve this problem. And let me walk you through the solution that we came up with. So what we did with this problem is, instead of saying, okay, we're going to try to find the entire table, we're going to solve a different problem, which is to find a corner of a table. And the nice thing about finding the corners is there's many, many cells on a given sheet, and every single one of those cells now becomes a training example. Okay, and I'll walk through how we built the network that does this, but this will illustrate two things. One is it'll illustrate how we solve this particular problem, but it also illustrates how all people who build neural networks have to think about how, what problem they're trying to solve, and can they solve the problem that they're trying to solve. So first of all, you do have to start with lots of labeled data. In our case, we have thousands of sheets, a couple thousand sheets that we hand labeled. What we do in the case of all neural networks, you have to have a signal. So in our case, we looked at the cells and we built representations of the contents of every cell. So things like what is the font? What is the font size? Is it underlined? Does it contain a number? And so all these different, what is the fill pattern, et cetera? All these different characteristics were labeled for every cell. From that, we created an abstraction. And in this particular case, we had 51 parameters per cell. And the next step is really a learn from image processing, the sort of building neural networks around image processing. Then we ask the following question. If we take the cells around a given cell, like a neighborhood, like a 10 by 10 square, can we use all those cells to predict what the value in the middle is? And how good can we do at that? So what do we mean by the value in the middle? Well, what we're trying to do is classify. So for example, you see the little rectangle up there. We're trying to classify, well, what is that thing in the middle? Is it one of the following? And here is the different categories of what we're trying to classify. Is it the top left of a table? Is it the top right? Is it the header bottom left or right? Don't worry about the headers. Is it the bottom left or the bottom right? Or NA, which means, no, this isn't a corner at all. This is definitely not a corner. And so you can see when we give that input to our neural network, it comes back with this classification that says, hey, the top right is a strong signal here. None of the other ones are very strong, but over 60% it thinks that's a top right. So what we said was we're going to change the problem to be looking for corners, but of course looking for corners is not the same as finding tables. You actually have to decide what corners go with each other to actually know where the table is. And so we have a post-processing phase, which is also the case in many applications of machine learning, where we have to decide, we have to create an algorithm to stitch together corners. And then we get a table. So then we decide where the whole table is. But let me show you in practice kind of what this looks like. This is a similar table to the one I showed earlier. And the colors here now are meaningful with respect to what our neural network thinks about every cell. So a dark blue, the darkness indicates how strong the signal is, and the color, like blue in this case, is a signal for a lower left, lower right corner. Likewise, the pink is a signal for an upper right corner. So you can see there's clearly some cells that have a strong signal, and then other cells which have a weaker signal. Like this could be maybe it's a bottom left header or bottom right header, but the point is it's not very strong. So this is probably more likely the case. And once we have this, as I mentioned, then we have to have a stitching process that actually decides where the tables actually are. And in this case, it's determined that these are the tables. In effect, these are the rows and columns that form the headers of the table. And that's Project Jura. Now, let me just talk a little bit about this problem as a challenge problem, because unlike some of the existing efforts around building neural networks, we have an interesting domain in the sense that we often neural networks either look at images or look at text, or maybe look at images and text together. But here we have what we call a multimodal domain. And what do we mean by that? Well, first of all, there's visual information, which that's why we use the convolutional neural network, is to basically understand what the spatial relationships are telling us, and what the choice of fonts, et cetera, is telling us. But on top of that, there's natural language. Every table contains text. And from the text in the headers, if it says total, you can infer quite a lot about what the cells in that row or column should be. And finally, there is code. And as we mentioned, there are formulas, and the formulas reference other cells. And that code then is also a signal to tell you what the intent of the person writing the code was, what things are related to each other, et cetera. So bringing all these different signals together into a single machine learning model and using it to understand spreadsheets is really a challenge task, and it's kind of forms the core of our approach to understanding spreadsheets. Okay, so I'm done with the sort of discussing our approaches to understanding spreadsheets, building tools for users that help them work with spreadsheets. Now I'm going to expand a little bit to talk more broadly about data. And I say spreadsheets, but a lot of the tools that we're looking at actually are about reasoning about tables. And tables are way more common even than spreadsheets. So for example, you just go on the web, you can find thousands of data sets that contain CSV files or PDF, et cetera. Go to Wikipedia. There's thousands of tables in Wikipedia telling you about everything you want to know. Who won the World Cup, et cetera. There's online. There are millions of PDF documents. There's many company reports, all of which contain information, information much like the tables we saw in the spreadsheets. And of course, some of these things, just like in the spreadsheets, are computed. And so, you can ask, well, is that computation correct? Did they make a mistake? And finally, we see even more of this. Google recently announced building basically a repository of data sets and an index, so you can very quickly type in search terms and find data related to those search terms. So there's a tremendous amount of data, and the argument I'm making is that the tool, we can get that data. The question is, what are the tools that help us really work with it, to do good things with it and to do it correctly? In fact, there's an argument you can make in this case where the amount of data in the world that's being collected and stored is increasing dramatically. So this is one, I guess it's a IDC report, whatever, about projecting out to 2025, basically showing the amount of data in the world. And it just increases exponentially, right? I mean, and realistically, the amount of code that's being created is not exponentially growing. And in fact, at some point in time, this is kind of my joke, that the code will be totally overwhelmed by the data. And so the data really is everything. And the code is important, but it's a tiny fraction of all the things that you have to think about. And in fact, this was the focus of an article, kind of forward-looking article in Wired about the end of code. Are we done writing code? And instead of writing code now, are we going to do things like I showed you with the table detection process? We're going to train models. And the thing that we use to do most software, the things that software does now, are not going to be by handwritten code, but in fact by training, by collecting data and training models. But when we step back and say, well, maybe that's not the whole picture. Maybe we're still going to write a lot of code. But even if it's a small part of the future, it's an important part of the future. And we have to think carefully about what tools those people using all that data need to do it right. And just like we think about what tools do software engineers need, to find bugs, we don't want to have security vulnerabilities. We don't want to have cases where the program crashes, reliability issues. In the same way, when we build software that leverages machine learning or AI, we have to think about what data was used to train that software, and are we doing the best we can? What are the best practices around working with that software? So, for example, we want to understand, where did the data come from? This is a fundamental question. And of course, there are all kinds of rules about what data you can and can't use. And we need, any developer who incorporates data into training for a model that accompanies software has to basically answer these questions. There's a lot of concern around building AI models around the issues of bias and fairness, which is to say, if the data has implicit biases in it and we build models from it, then those models themselves will have the same bias. Likewise, there's a security problem around individuals who intentionally poison data. So in that case, you can have a situation where somebody knows that you're going to use the data that they provide for training, and they intentionally make it bad in some way so that it will make your model performing correctly. Of course, just having that data becomes a challenge compared to software. You may have 10 megabytes of code in a repository, but it may be terabytes of data is used to train a model to be part of that software. And so how do you do version control on the terabytes? How do you share it, et cetera? Of course, privacy is a fundamental concern. When you have so much data, you have to worry about, does it contain personal information? Did you make sure that you got rid of all that? Or if it does, how do you avoid that personal information somehow leaking into the model in such a way that a clever person can then later extract it? So this question about how much of that training data is embedded in the model, how much can be extracted by an adversary, becomes a fundamental concern. And that's got to be part of every piece of software now that uses data to build machine learning models. There's another concept called data drift, which is to say, when we use data to train a model, and then later we use that model to predict something, how do we know that the inputs that we get when we're using it for inference actually are close to or like the data that we use to train it? And if there's this drift and it's quite different, then the performance of our model will now all of a sudden not be as good. And we have to worry about, how do we maintain an understanding of that? How do we fix it? even the question of like, how do, once we know that the model's out of sync, like, how do we redeploy it? What are the circumstances under which we can, deploy improvement of the model and know that it's going to be an improvement across the board? Of course, in the end, there's biases in the input data. There's also biases in the model itself. And so you have to ask questions like, is this model, even though it may have 90% accuracy, is it 90% accuracy across all individuals? Say if it's doing face recognition, are there a subclass of individuals for which it performs poorly? You have to understand these things. And finally, and I think this is an open space in the sense of challenges for people working in this, on tools, is like, what are the opportunities for adversaries here? Like, how easy is it to create an adversarial input? How do you build the software in such a way that it's robust so that when people try to, give inputs that are intentionally going to give the wrong answer, you can detect that, or you can at least, protect against it. So these are all incredible challenges. I just hope that the whole community can embrace these challenges, because it's going to be now and increasingly a fundamental part of every software system. So you can step back and say, well, wait a minute, if these are all these new problems, maybe software engineering is obsolete. Maybe we don't need any of that old software engineering. Everything's about this data. And let me just say, look, AI fundamentally is still software. The whole process involves both a combination, as I mentioned with the Jura example, a combination of the training and the model, but also after the model runs, you have to do some other things. So in the case with table detection, we had to stitch together the corners. And I think you can see this paralleled in what Microsoft has published now as its concept of AI principles, these are fundamental principles that are true for AI models and software that uses AI. But also, when you step back, you realize, well, these are just things that you want all software to have that property. It's not just AI software. It's all software. And fundamentally, all the concepts around reliability or privacy or transparency are all things that we have to think about across the board, both with software that uses AI and software that doesn't use AI. So the answer to is it obsolete? Well, the answer, in my opinion, is no. But here's an even sort of more important point, which is that the stakes are high. The kinds of expectations that people have around building software really have grown dramatically in terms of the kinds of problems, the kinds of support that they can give to humans, the kinds of challenges in the world that it can help solve. And so Ed Lazowska has this very nice graphic from 5 to 10 years ago now, but highly relevant still, is the notion that historically computer science has really thought about sort of core issues like operating systems or databases or hardware architecture. But as we look, in the last 10 years, in the last 20 years, the sort of impact and the kinds of things that computer science has been applied to is just broadly increasing. So big data is a general category, cloud computing a general category, but they're not necessarily in the core. They're sort of, I take operating systems, but then I have to say, well, how do I deal with 100,000 computers in the cloud? And I want to manage all of those. Similarly, NLP it's part of the core AI, but it's a very specific problem that even if you solve that one problem and not the general problem, you have a tremendous amount of impact. And beyond these expansions of the core, there are all these different application areas for which we now see computers playing a fundamental role. So we're actually saying now we can transform all of scientific discovery in using these new approaches, and doing it with computers is a fundamental part of that. Same with energy and sustainability. If we want to build a world where we can have sustainable energy, we need to think about how computers are going to help with that problem. Okay, so I'm almost done. I appreciate your patience and time. One of the things I want to say is, let's just start with what is a program? Like, we think about developers, software developers, we think about code, that's a program. But let me try to expand your view. I'm going to argue that a spreadsheet is a program. I'm going to argue that a programming by example illustration of, like, I want to transform this thing to that thing, now build a program from that. That's code. That's a new kind of code. It's examples instead of if statements, but it's still code. And finally, the AI model where you have 100,000 images and you're generating something that recognizes cats in those images, that's also a new approach to programming. and fundamentally has many of the same issues that we have always had with programming. So who is the programmer in this case? Well, it's certainly not professional developers. It's really a broader set of people. I call it the Grow Dev movement, where you have more people participating, needing the tools, and basically trying to leverage these computers to do more and more important things. So just to summarize in a very concise way, I think we have to have new tools that connect non-programmers in an intuitive way, because we really need to think carefully about how to make it easy, how to avoid having people make mistakes, all the things that we want to have in quality software. And then we have to think about understanding both the code and the data, because fundamentally ignoring the data, not understanding what the data, how much impact the data has, will not be a good thing in the future. All right, so let me just say, just a final note. I really want to push this notion of broadening the view of who's a programmer. I want to broaden the view of who needs these tools. And I think one of the messages here is we need to get, if we're in the software engineering community, we need to get outside the box and start talking to people that aren't other coders, aren't other programmers. Talk to the people working with data. Talk to the people who are trying to do, science. And get an understanding from them of how the things that we need in our software development process could be broadened to help them as well. So understanding workflows, doing a vertical, really understanding the tasks, etc. So, and let me just basically emphasize the aspect of human-computer interaction. So in this particular case, it's not that there's just some piece of code that's syntactically correct. A lot of the subtleties of how you work with people and give them tools is to understand what their understanding is, what information you're giving them, and how that is going back and forth to help them solve their problem. So I think we can't capture everything mathematically. One of the things about spreadsheets that we've learned is that there are aspects of spreadsheets which are about human-to-human communication, and we can't find formal ways to characterize that. We have to actually use statistics and machine learning, et cetera, to understand that. And with that, I'm done. I want to thank you for your patience and for your interest. This is my work, not just my work. It's actually the work of many individuals who I've worked with, and I've done most of the heavy lifting. If you want to sort of follow some of my thoughts or insights, I occasionally post to Twitter, and you can follow me there. The slide that I showed from Ed Lazowska is actually, I got contact with this through an organization called the CCC, which is a Computing Community Consortium, which is a group of, it's a council that looks at patterns in computer science research and tries to help predict future patterns. And so there's a website, and they have lots of interesting material there about the future of computing. With that, I thank you.
Hello, everyone. Thank you so much for attending the seminar on the future of data programming. It's been a great pleasure to present it, and I'm happy to answer some questions. I'm Ben Zorn. I work at Microsoft Research in Redmond, and I'm going to be answering questions over the next 15 minutes. Some of the questions that you asked in the stream, and also other questions that I've had. So in terms of some of the thoughts that we've had around programming with data, I think one thought is how many other kinds of technologies around helping people, say, with spreadsheets, can you think of that go beyond just finding bugs, which is one of the things I mentioned in the talk. And there are a number of ways that you can imagine helping people, not just in spreadsheets, but also people working with any kind of large data sets. Some of those are basically understanding patterns in the data and helping people identify those patterns without them explicitly exploring. So data exploration, the data analysis involves an exploratory phase, often involves a human trying this, trying that, basically experimenting. And one of the things we can understand is how to accelerate that process, how to bring the human into the loop, but at the same time give them insights more quickly. And so one of the technologies I didn't mention in the talk, which is actually quite important, is Excel has already a feature called Ideas where it appears, it's a new panel that appears as you click on the Ideas button, and it will basically show you things about the data set that you have in the current sheet that help you essentially get insights into what's going on. So for example, it might suggest a trend that's in your data. It might suggest a chart, recommend a chart that could be created from that data. And so these are things that augment a person. They augment our ability to understand what the data represents, but at the same time, they give us, they accelerate our ability to quickly see those insights and act on them. Another dimension of the kinds of things that people working with tools face, spreadsheets in particular, is really managing the whole process around creating spreadsheets, sharing them, updating them, etc. And in particular, a number of people would get value out of better tools that help them understand where the data in a spreadsheet came from, or if the spreadsheet gets changed over time, what changes were made, and who made the changes, and why the changes were made. And so, just as we see in the software development process, where you have code reviews and you have powerful version control that gives you insights quickly into sort of why things were done or how things were done, I think tools around helping people manage data that shares that experience, that allows people to answer questions about why or what was modified or where did this data come from. These are tools that will benefit more and more people in the future and are valuable. Another question is, how do we expect these tools that developers use to support data programming? And one of the things I in the focus of the talk, I focused on non-developers and sort of how to give them a set of capabilities that would accelerate their ability to work with data. But in fact, there's also many developers have a lot more data in their process. So for example, as I mentioned, many of them are now incorporating AI models, et cetera. And I think we're just learning how to incorporate new tools that understand data, understand AI models into the development process. So support for AI and machine learning workflows, is increasing. You get, in cloud computing in particular, configurations like Azure ML give you tools that help you incorporate the kinds of analyses and the kinds of workflows that take data from one source, transform it, and then feed it into a machine learning model, and make that a capability that's quite easy to do relatively seamlessly, basically by people connecting things and not necessarily having to write a lot of code that opens files, et cetera. So you can imagine a significant improvement in the ability for people to very quickly have an entire workflow. And then within that workflow, a new capability, as I mentioned in the talk, it comes around things like learning, like fairness. So in fact, there's a capability that Microsoft Research has released called FairLearn, which helps people who are involved in the development of artificial intelligence assess their system's fairness. And basically, these are the kinds of new things that developers have to think about, and tools like FairLearn are a starting point to help them do that. As organizations get more experience to understand the process of AI development, I think what we'll see is a sort of a progression from starting with just an understanding of the right guidelines, like what do we think about, how do we think about the challenges. Then beyond the guidelines and best practices, we'll start seeing them embodied in tools like FairLearn that then allow you to automate part of the process. Another question that came up was, how can people, that aren't on a pro dev sort of education path, take advantage of some of these capabilities? And I think a couple things to mention. One of the most important is that increasingly almost every kind of major has a component of it that involves some capability related to getting data or understanding data. And so understanding data through statistics, or taking classes in data science that introduce you to the tools, as I mentioned, things like the R programming language, or the tools in Python, the Jupyter notebooks, et cetera. These are all capabilities that allow you to get started working with data relatively easily, there are many resources on the web related to understanding how to build notebooks, how to experiment with data, and to really explore the data in deeper ways. The existence of many Python Jupyter notebooks and the documentation that goes along with them, explaining to people the process and sort of doing step by step. There's many YouTube videos, for example, that help you walk through how to use tool sets that give you this kind of capability. As a final question, I think one of the things that I hear a lot is people asking sort of, where we are now, like what will programming be like in 10 years? And if you think about 10 years ago, well, people were writing code, but I think a lot more people now are doing things, as I mentioned, like training machine learning models. There's a lot more data science. It's really become a major part of the computer field. And I think, as I mentioned in the talk, one of the most important aspects of the future is going to be the degree to which data is an integral part. I think we have a question about how we share that data. I do think that increasingly we're seeing more and more data available, and the ability to combine the data in new ways and to mash up data in different ways to really see and understand things beyond correlations. One of the challenges in understanding data is understanding the difference between causation and correlation. And fundamentally, if we can find better strategies to understand causality, to say, the reason that we observe this correlation is because this is a cause that achieved that effect, those kind of tools that help you tell the difference between correlation and causation will actually, I think, be very valuable and increasingly available in the future. Certainly, we're going to see significantly higher ambition. We definitely have a huge opportunity in this space to think about problems that we never were able to solve in the past. And I think if I could tell you what the most exciting areas in that space would be, I would be able to take advantage of that. But I just have to say, I think ultimately, the opportunity to make the tools and the data available to so many people is really guarantees an amazing amount of innovation and new discoveries, new applications that we just can't even think of right now. So the ability of non-programmers and individuals to take advantage of this data, both in terms of doing analysis, understanding causation, et cetera, and also of being able to construct AI models. I do believe that in the future, the ability to get labeled data and to use unsupervised learning, et cetera, to create models for non-experts will become more and more important. And I think we're just at the beginning of understanding how to do that well. So with that, I'd like to thank you so much for attending. It's been a real pleasure to talk about my work and the great opportunities that are available. If you're interested in learning more, we have resources on the resource list on the screen, and certainly I encourage you to, if you use Excel and you're interested in trying out ExceLint, I definitely encourage you to go to the website and check that out. And overall, I definitely encourage you to engage with resources on the web related to using tools that exist in terms of our notebooks. Our Studio and Python notebooks to really explore data and to learn how to manipulate it and to extract ideas from it more effectively. So thank you and have a great day.